If you ask most physicists when they first started doubting reality, the answer usually comes back to the same thing: quantum mechanics. It's the theory that changed everything. Not because it added new details to our picture of the universe, but because it completely rewrote the picture itself. It didn't just tweak the laws of nature. It made us question whether nature has laws in the first place, or if what we call laws are just patterns that only emerge when we're watching. At its heart, quantum mechanics is a set of rules that describe how the tiniest pieces of the universe behave. Electrons, photons, neutrinos, the basic ingredients of matter and energy. But when physicists began observing these particles closely, something bizarre kept happening. They refused to act like objects. Particles didn't move in clean paths. They didn't sit in one place. They didn't have definite properties. Instead, they seemed to exist in a haze of probabilities. Not in one state, but in many. Not in one location, but in multiple. Not as definite things, but as possibilities. The only time they decided to be anywhere or do anything was when someone measured them. And that's where everything started to unravel. Take the classic example, the double-slit experiment. Fire individual particles, like electrons at a screen with two slits, and they somehow create an interference pattern. Not two clusters like you'd expect if the particles just flew through one slit or the other, but a wave pattern, like the particles went through both slits at once and interfered with themselves. That makes no sense, unless you stop thinking of the electron as a particle and start thinking of it as something more abstract. A wave of potential outcomes. Now here's where it gets weirder. Add a detector, a simple measurement device to check which slit the electron goes through, and suddenly the interference pattern disappears. The particle chooses a path. It behaves like a single particle again. The act of observing it changes the outcome, and not just in a vague, poetic way. It literally changes what the electron does. So, what's real here? The particle, the measurement, the pattern, or just your choice to look? Physicists tried to explain this away. Some said the wave function, the math describing those possibilities, was just a tool for prediction, not a real thing. Others weren't so sure, because the math worked too well. It wasn't just useful, it was precise. It predicted outcomes with accuracy no other theory ever matched. So maybe the wave function wasn't just a trick. Maybe it really was the thing, in which case the universe at its core isn't made of particles or matter, but of probability. That's not speculation. That's the backbone of modern quantum theory. When you calculate what an electron will do, you don't get a position. You get a wave function, a spread of outcomes. You don't get one answer. You get a cloud of potential answers. And it's only when you make a measurement that one of those outcomes becomes real. But what does that mean? That there wasn't an electron until you looked? That it had no position until you asked the question? Some physicists tried to avoid this by introducing hidden variables, invisible properties that the particle really had, but we just couldn't see. The problem? Those theories got destroyed by actual experiments. In the 1960s, physicist John Bell came up with a test, a way to check whether reality was hiding some deeper layer underneath quantum mechanics.